Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, 2017 question 2, paper 1 was a complex number question. Z was equal to minus root 3 plus I, where I squared is equal to minus 1. Use De Moivre's theorem to write Z4 in the form a plus b root ci, where a, b and c are integers. Okay, so using De Moivre's theorem. So if we go to our log tables, page 20, we can see De Moivre's theorem is given to us. So ignore this part. This is De Moivre's theorem here. It tells us that when we have a complex number in polar form to a power, we multiply or by the power, we raise or to the power of n, and we multiply the angle by n. Okay, now I'll come back to that again, but the first step always in applying De Moivre's theorem is to make sure that your complex number is written in polar form. Okay, so that's the first thing I'm going to do. I'm going to take this, which is in Cartesian form or rectangular form, and I'm going to write it in polar form. Okay, so I always start this with doing just a rough graph of the Cartesian plane. So there's your real numbers, your imaginary numbers, and I'm just going to plot a dot on which quadrant minus root 3 plus I is in. So minus root 3, I come over here, plus 1i, I go up here somewhere. Okay, and I don't have to be in any ways accurate with that. All I'm trying to figure out is what quadrant I'm in so that I can figure out my angle. So your angle always starts with the positive sense of the x-axis. So that is the angle that I'm going to need for my complex number. Okay, so to work out, so remember what polar form is. Instead of describing it as minus root 3 plus I, I'm going to describe it in terms of how far out are you from the origin, and how many degrees are you away from this starting line, which is the positive sense of the x-axis. So it's a different way to describe this location. How far out are you from the origin? How far in angle are you from the positive sense of the x-axis? Okay, so the first thing I'm going to work out is or, which is how far are you out from the origin. And to do that, it's the square root of, if a complex number z is equal to x plus yi, okay, how far you're out from the origin is the square root of x squared plus y squared. So look that there's no I in when you're calculating its distance. The I is just telling you which is x and which is y. So it's the square root then of my x is minus root 3 squared plus, and my y is the number in front of I, which is 1 in my case. So that's going to be the square root of 4, which is 2. Okay, so this complex number is a distance 2 out from the origin. This is indeed Pythagoras' theorem, and what you're using is the triangle that you form with the x-axis. Okay, there's your minus root 3 out, and there's your distance of 1 up. Okay, your angle, I'm going to call it a reference angle. It's going to be the tan inverse of y over x. Now, let me explain why I'm calling it a reference angle and not theta, because again, if I draw a bigger version of my complex number, just to explain it a bit better, there's minus root 3 plus I. Let me form my triangle again. So my triangle is here. Okay, so can you see when I draw the triangle, actually draw it onto it? And you always draw your triangle with reference or with respect to the x-axis. It would never be drawn with respect to the y-axis, which would give it that one. Okay, it's always with respect to the x-axis. Can you see when I draw it, actually draw it in there, this is the angle that's in my triangle. Okay, not the theta I need for the location. Okay, so that's why I'm calling it a reference angle. It's equal to opposite over adjacent. So it's equal to 1 over root 3. And if I put that into the calculator, I forgot my tan inverse, didn't I? Not tan inverse at all. Tan of 1 over root 3. I will get my calculator to work yet. Yeah. I do indeed get my 30 degrees. Okay, I just couldn't work my brackets on my calculator there, a little blonde moment. But anyway, so I get 30 degrees for that angle. Okay, so in here, right in here, is an angle of 30 degrees. Okay, so you can visually see then that to work out this angle, I would subtract it from 180 degrees because there's a 180 degree angle there. Okay, so therefore theta is equal to 180 degrees minus that 30 degrees, which is 150 degrees. Or you can know by heart that if you're in quadrant 2, so this is quadrant 1, this is quadrant 2. If you're in quadrant 2, you are always going to subtract your reference angle from 180 degrees, whether that's in the complex number chapter or that's the trig chapter. Okay, so therefore now I can write my complex number, which is minus root 3 plus I, as, remember what it's telling me, or cos theta plus I sine theta. Okay, or cos theta plus I sine theta. So I'm going to fill it into this. So it is equal to 2 times cos 150 degrees plus I sine 150 degrees. Okay, could you have written this in radian form? Yes, of course. Okay, so in radian form, you would have got theta being equal to, let me just work it out there now for you. A sixth pi. Well, I should call that the reference angle to match the lingo that I used. That's my reference angle. So theta is equal to pi minus that, so 5 over 6 pi. Okay, so whether you do it in radian mode or degrees, it doesn't matter when they don't say. Okay, now many teachers I know always do it in radian mode. Okay, so go with whatever your teacher guides you to do. So that's it written in polar form. So once it's written in polar form, I can then apply De Morvis's theorem. Okay, so what I want to work out now is z to the power of 4. So that's equal to 2 times cos 150 degrees plus I sine 150 degrees, all to the power of 4. And if you can follow the log tables, De Morvis's theorem tells you to do or to the power of 4. Do you see that? So let's do that. That's 2 to the power of 4 cos n times the angle. So I multiply the angle by the power. So it'll be 4 times 150 degrees plus I sine, and I do it here as well. So that's how you apply De Morvis's theorem. Okay, so I hope that makes sense. You can tidy it up and you get 16 cos of, I'm going to put down 600 degrees and I'll come back to that now in a second. 600 degrees. Okay, we generally, when you're leaving an angle in a question, you generally don't write an angle as greater than 360 degrees. Okay, so the reason for that is if I draw any angle, it's this angle here. Okay, so 360 degrees is one full revolution. Okay, so if I'm standing at this point, can you see I can do a revolution and I come back, I'm going to still be at the same angle with respect to the x-axis. So what you normally do is subtract out the 360 degree revolutions from a big angle as such. Okay, so I could write him as 240 degrees. Now, it doesn't particularly matter in this question because you were asked to give your form in back to rectangular mode, okay, or Cartesian mode, okay, which is this one. So it doesn't really matter whether you leave it as 600 or you convert it back, you take out the full cycles. So leaving it as 600 degrees, because I think it's how most people would do it, I'm putting into my calculator 16 times cos 600. And for that, I'm getting -8. And then into my calculator, I'm putting 16 times sine 600 degrees. And I'm getting -8 root 3i. Okay, so you can see now that it's in the form a, there's your a, plus b root c, and I have that there. So that is in fact your answer to Z4. Okay, so I hope that makes sense. If they had asked for my answer in polar form, I would have left my answer as the following: 16 cos 240 degrees plus I sine 240 degrees. Okay, but they didn't ask for it in polar form, they wanted it in rectangular form. So I hope that makes sense. That was worth 15 marks for this question, so it shows you how important it is to be able to convert to polar form for a start, and then to be able to do all the applications of De Morvis's theorem. Okay, part B then of that question was as follows. The complex number W is such that the modulus of W is equal to 3, and W makes an angle of 30 degrees with the positive sense of the real axis. If T is equal to ZW, write T in its simplest form. Okay, so what does that mean? Okay, when I'm going to draw my Cartesian plane here. So there's my real axis, there's my imaginary axis, and it's telling me that this complex number, the distance out from the origin, that's what that means, is 3, and it makes an angle of 30 degrees with the positive sense of the real axis. So these are the positive numbers of the real axis, these are the negative numbers. Okay, so it's always, this is where we always start. So it makes an angle of 30 degrees. Well, that's about 90, so about a third of that would be my 30 degrees. So let's draw him in and let's go out a distance of whatever we think 3 is. Okay, so that is the complex number W. Okay, so it's a distance 3 and it's an angle of 30 degrees. Okay, so I'm hoping when I write it like that, that you can see now that I can simply put down that W is equal to 3 cos 30 degrees plus I sine 30 degrees. Okay, so I hope that makes sense. Right. And then it says if T is equal to Z times W, find T basically. So I have to multiply these complex numbers together. So I want to do a couple of things in the complex numbers. I'm going to use this question to show you a couple of things about De Morvis's theorem as revision, or for you to learn. Okay, really handy little tips and tricks. Right, the first thing I'm going to show you is, well, we have to go back and we have to find our z. Okay, so our z was equal to 2 cos 150 degrees, I think, plus I sine 150 degrees. Let me just double check that. So 2 cos 150 plus I sine 150. Okay, so the first thing I'm going to do is multiply them using polar form. Okay, polar form was specifically invented for this type of thing, for computation, for doing powers, for multiplying, for dividing, and so on and so forth. So I want to show you how easy it is to multiply two numbers in polar form. So the rule is, if you multiply two complex numbers, you multiply R1 by R2, and you do cos of theta 1 plus theta 2. Plus I sine theta 1 plus theta 2. Okay, so to give some English on that, if I'm multiplying two numbers that are in polar form, I multiply their moduluses together and I add their angles. Okay, so therefore t is equal to, let's multiply the two moduluses together, 3 2's are 6, bracket, cos, let's add the angle. So I have 30 degrees plus 150 degrees, so 180 degrees plus I sine 180 degrees. Okay, it says to write it in its simplest form, which is Cartesian form, rectangular form, whatever you call it. Cos 180 gets called both, so that's why I keep using both. So 6 times cos 180 degrees is minus 6. 6 sine 180 degrees is, of course, 0. Okay, so in its simplest form, that is equal to minus 6. So that's the first thing I want to show you. How do you multiply two numbers in polar form? Multiply their moduluses together, add their angle. Okay. Second thing I want to show you, which is kind of related but different, if you were told to divide two complex numbers in polar form, you won't be too surprised then to hear that it's R1 divided by R2, cos subtract the angles. Theta 1 minus theta 2. Okay, assuming the one on the top is your R1 and your theta 1. Okay, so that's how you subtract, that's how you add, and of course, that's how you do powers. So roots is the fourth question that they ask on De Morvis theorem. Okay, now there's something else I want to show you, which is as follows. If it's okay, I'm just going to copy the question as such. Okay, what happens if you had, well, we have W written down, okay, and we had figured out he was 3 cos 30 degrees plus I sine 30 degrees, okay. Christian name, surname is the order they go in, Christian name before surname. What happens if you had worked out Z, the complex number, and you had written them in radian mode? Okay, how do you convert? Because you can see there's no way you can add a radian angle and a degree angle together. Okay, so how do you convert one to the other? So you have two choices to convert degrees to radians. Take the degrees, the 30 degrees. What fraction of 360 degrees is it? Because 360 degrees is a full cycle, and apply that same fraction to 2 pi, which is the equivalent of 10 360 degrees, okay? So 30 over 360 multiply by 2 pi. And you get 1/6 pi, okay? So you could change him to 3 cos a 6th pi plus I sine a 6th pi. That's how you convert from degrees to radians, okay? So then to convert from radians to degrees, it's the same but backwards, okay? Let's convert him to degrees. So you'd go 5 pi over 6. What fraction of 2 pi is that? And you'd multiply it by 360 degrees. So how I remember it is, if it's in degrees, you put it over degrees and you multiply it by the other one. If it's in radians, you put it over radians, which is 2 pi, and you multiply it over the other one. Okay, and I think we've established that that is 150 degrees. Okay, so that's the second thing I wanted to show you was if you need to convert from degrees to radians or radians to degrees at any stage, this is how you do it. Okay, was there another way to do this question? Absolutely there was, and some of you may have done it. Okay, nothing wrong with taking W being equal to 3 cos 30 degrees plus I sine 30 degrees, converting that to rectangular form, 3 cos 30. So that's 3 root 3 over 2 plus I 3 sine 30 degrees plus 3 over 2i. Okay, and then when you had to work out z times w, you were going 3 root 2, 3 plus 3 over 2i, multiplying by whatever z was in rectangular form, I can't remember, minus root 3 plus I. Okay, and doing this by this, this by this, this by this, and this by this, and multiplying them out in Cartesian form. Nothing wrong with that as well. You will get minus 6. Okay, so just using that question to show you a few different things about complex numbers. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.